we are going to do 6.3, day 3. Do you like green Skittles? In 2013, Skittles changed the flavor of green from lime to sour apple. Big mistake. I agree. Mr. Wilcox takes a small handful of 5 Skittles from a bin of 10,000 Skittles and gets all green. If 20% of the Skittles are green, what is the probability of this happening? Is this a binomial setting? So let's talk about this. We need to check bins, B-I-N-S. Binary, in this case, you get green or not green. So there are 2 options. Each Skittle is independent of one another. N, it said you took a handful of 5, so N equals 5. And same probability of success. Not really in this case because he didn't put them back. So no, not really due to no replacement. So in this case, this is not necessarily binomial because you're violating that S condition. So number 2 says find the probability of getting 5 green if this is not a binomial setting. So in this case, we would get, if there are an even amount, there would be 2,000 green in that bag of 10,000 Skittles, since there's a 20% chance of them being green. So that would be, in this case, the probability of all 5 green would be 2,000 over 10,000 times 1,999 over 9,999 times 1,998 over 9,998 times 1,997 over 9,997 times 1,996 over 9,996, and that equals 0.00319. 0.00319. Find the probability of getting 5 green if this was a binomial setting. Think of the binomial formula. So the probability of all 5 green, if it were binomial, would be probability of all 5 green would be 5 choose 5, and that would be 0.2 to the 5th and 0.8 times 5 minus 5, which would be 0. And then that would be 0.00320, which your answers in 2 and 3 are really close. So they're almost the same, are super close. And this happens because the sample size is so small, yet the population is so large. So if we check our 10% condition in this case, so that would be 5 times 10 equals 50. That is way less than 10,000, right? So our 10% condition actually checks out here, which then allows us to check off that independence condition, thus saying that the probability of success is basically the same, because even if we took out one of the Skittles, it's not really changing the probability of green from time to time. So now Mr. Wilcox now grabs a huge handful of 100 Skittles and X is the number of green Skittles in a handful of 100 Skittles. X can be considered binomial because that 10% condition is still satisfied. What is the probability of getting at most 11 green Skittles? So because if we were trying to find this at most 11 green Skittles, we would probably want to use binom CDF. And there are calculator function videos on that. So remember, binom CDF gives you everything that number and below. So that would be binom CDF. N would be 100. Probability of getting a green is 20%. So 0.2 and 11. So 11 and below gets you 0.0126. It would take you a long time to do all 11 of those and add them up if you wanted to do that by hand. From here, what is the approximate shape? As we can see that this is looking pretty normal in this histogram. And we can check that using our normal condition. N times P has to be bigger than or equal to 10, and N times 1 minus P has to be bigger than or equal to 10, like we dealt with proportions. So N here is 100. 100 times 0.2 is 20, which is bigger than or equal to 10, and 100 times 0.8 is bigger than or equal to 10 as well. Now, if we were to calculate the mean and standard deviation, remember if we're approximating binomial, the mean is N times P, which is 100 times 0.2, so the mean would be 20. And standard deviation is the square root of N times P times 1 minus P, which is 4. Which that would come from the square root of 100 times 0.2 times 0.8, and that equals 4. If we were to do this problem to find this number, what is the probability of getting at most 11 green Skittles using the normal distribution? We would have to find a z-score. So z would equal 11 minus the mean, which would be 20 over 4, and that would give us negative 2.25. Oh my goodness, my dog is dreaming. Carmen! And then I look that up. The probability of that's 0.0122, and as you can see, these two numbers now, this number here and this number here, are almost the same because it's the normal approximation of a binomial distribution that says if this checks out from number 6, N times P is greater than 10 and N times 1 minus P is greater than 10, we can actually use the normal distribution to find those probabilities instead of using the binomial distribution. All right, moving on to these, moving on to your quick notes. The 10% rule, remember that can prove independence. So remember 10% rule is N times 10 is less than your population. Can prove independence. And then our large counts condition can allow you to use the normal distribution for a binomial model. So that's N times P has to be bigger than 10, and N times 1 minus P has to be bigger than or equal to 10. All right, let's take a look down at this, check your understanding. You basically can say why it's can be modeled with binomial, and that is done by checking that independence condition. Use a binomial distribution to estimate the probability of 50 or fewer. So remember, you can use binom CDF for this. And justifying why it can be used as a normal distribution. This is where your large counts comes into play. And actually using this, remember, you need a z-score. So there are some little hints for that. All right, and that is the end of lesson 6.3, day 3.